Roman is not here, but I will, nevertheless, I will start with the question he asked me. So there is a one-sided version of Hardy's theorem, which says that, say, if f of x is of capital of to the power minus 3 x squared at the side is of capital to the power minus b size square and a b bigger the way I formulated than some numerical constant, then f is identical. So the difference that when x tends, say, to plus infinity, it doesn't matter, it could be on different half lines. So the difference is that here we assume only one-sided decay of the function. And in the homework, in second homework, I gave this question, which yields some not sharp value of C0. And Roman asked me what is the precise value of C0. For some reason, I thought that this is difficult, but C0 is the same pi square. And I will explain why. So this is, it doesn't say Hardy's theorem said the way I formulated what happens in the critical case when product equals pi square. Well, I've put pi here and pi there in the proof. This I am not saying what happens in the critical case, but still in the supercritical case, we have uniqueness. And I will tell you briefly why you don't need, the way I sketched in the homework doesn't give it, but instead of this, you need a better version or sharper version of Radchenko-Viazovska principle. I will formulate it only for half plane. So suppose f is analytic in the half plane. Continuous up to its boundary. Say assume that half plane is a right half plane. Suppose that f has the same a priori exponential bound. And that it decays fast on the boundary. With some positive b. Then f is a zero function. So if function of exponent which grows exponentially, decay exponentially on the boundary, it should be zero function. This is a slightly sharper version of Fragment-Lindelöf. You can get it from Fragment-Lindelöf, and if you apply it then not to the half plane but to the angle, then here you will have some powers. And copy the proof which we gave, you will get that f is zero. So this is how to get that sharp constant is the same pi squared. So I hope that Roman will see it at some moment. So now we return to Benedicks theorem.
Sorry, is in the last line on that board. So you have a to the yes, a e minus b absolute. Is it yi or is it absolute value?
Absolute value of y.
Ah, yeah, okay. I thought that is I, so sorry. Okay. Okay, thanks.
So now we return to Benedicks theorem. Which says the following, that if f is a function in L1 of RD, A is a support of F. Both F and F hat have finite supports of finite measures. Then F. So we will use lemma, which is a version of Poisson summation. I will probably write it here and we'll keep it here during the proof of Benedicks theorem. So lemma or exercise, which we will use, it suppose we have a function in L1, then the following holds, and we denote by Pf of x its periodization. Then the following holds: A, the series converges in L1 on the torus. Integral of periodization over the torus is the same as integral over the function. And Fourier coefficient, periodization is a periodic function, so we can write its Fourier coefficient in the Fourier series. So they equal the Fourier transform. I use here hat in two different, no, in both cases it's Fourier transform, but different Fourier transform. So now let us prove Benedicks theorem. So I will assume that length of A is less than 1. We can always rescale function replacing x by t times x, then psi will be replaced by psi over t, and condition will not be changed, but length of A can be done as small as we wish. And let us consider two periodizations. So first, periodization of indicator function of A. Oh, well, we know that this is length of A, which is less than 1. So it has a complement. Periodization of indicator function has important property. At each point, or almost every point, either it's either it's 0 or it's bigger or equal than 1. And we will use this property all the time. So this tells us that there exists a subset on the torus of positive measure such that periodization of 1A equals 0 on this tells us that for any, when I say any, I always mean almost every, or because we are in Lebesgue situation, f of x plus k equals 0. Right, because 1A was exactly support of f, and this was periodization. Periodization vanishes. This means that all these functions vanish. We can apply the same argument to on the Fourier side. When we integrate periodization of indicator function of the support of Fourier transform, this will be length of B. Finite measure. So what does it mean? It means that on the set of full measure, P of 1B well, it would be infinite. On a set of positive measures, then integral would be. So what does it mean? This means that for every psi from our set of full measure, psi plus k belongs to the set B only for finitely many case. Indeed, when we do periodization, we add 1, 1, 1, 1, 1, 1, 1 if we appear in B. So if we know that periodization is finite, this means that we had only finitely many terms, so other terms vanish. And what does it mean for Fourier transform? It means that for psi in 1, f hat of psi plus k doesn't vanish only for finitely many. So we are somehow in symmetric situation for on the set of positive measure, all shifts, integer shifts vanish, and on the full set, after some point, they also vanish. So what remains as we fix psi in TD and consider the function f psi of x. This is also periodization. F of x plus k. Is a power against the This is periodization of x times this exponent. What can we say about this function? So our function f was in L1. When we multiply by something unimodular, we're still in L1. So we know that by lemma that this function will be in L1. Fourier coefficients of the Fourier series for this periodic function, again by lemma. All this here I apply the lemma. This is the same as shifted by psi Fourier coefficients of f. Not just because when you multiply by exponent by e to the power minus 2 pi I psi times x, you shift Fourier coefficient by psi. But almost surely this guy vanishes. So we conclude from here that f psi is a trigonometric polynomial. The Fourier series of this function has only finitely many coefficients. Well, on our set of image. On the other hand, if we look here, f psi equals 0 on x. Well, every term of the series on x, every term of the series vanishes. So we have a trigonometric polynomial which vanishes on a set of positive measures. And by exercise which I gave you last time, this is a simple uniqueness theorem. This trigonometric polynomial should be. You can try first prove it in dimension 1, and then in any dimension you need to use a simple trick from measure theory that you will have many one-dimensional sections on which this polynomial. Well, we're done. Look, what did we prove? We proved that f psi vanish. So this means that Fourier coefficients vanish for all k. But this means that Fourier transform of our original function vanish for all k in ZT and for almost every psi TD. Well, by shifts of the set of full measure on the torus, we get the whole RD. So this means that Fourier transform vanishes almost everywhere on RD. Well, it was, our function was integrable, so this is a continuous function. So very beautiful, and proof not difficult, really beautiful, and this is an important fact. Maybe before we will leave this, I will make one comment. But if you have questions, please If you have questions, please ask.
So Misha, it does look like so you're getting contradiction to the trigonometric polynomial sort of has like positive measure zeros.
Yes.
Zero positive. It looks like it's like a huge overkill. There is a lot of room there.
But not in the direction.
Something say,
Well, because we use translation, we needed to cover, you see, we needed to cover in the end the whole, in that direction, there are, so there is, this is, all this is related very much to many other things, to things which are called today quite fashionable fractal uncertainty principle after Bourgain and Dyatlov and other things. There is indeed a lot of room for improvement, but I wanted to speak only about one place, one thing, the simplest one, that when we deal with uniqueness pairs, we deal with say function and Fourier transform vanish on some sets, then function is zero. But you can ask quantitative question. If function is small on some set and Fourier transform is small on the other set, where the function will be small, say in L1 and L2, whatever, in the space which we consider. And in Benedicks theorem, this is called Amrei-Berthier theorem, but for us it will be exercise. I think it says the following, that if length of sets A and B is finite, then you can estimate L2 norm, and F is a function from L2 on RT. Then you can estimate its L2 norm by sum of this. It's L2, I formulated Benedicks theorem for L1. There is a small difference, but you need to pay attention. And if you don't care how the constant depends on AB, and this was their formulation, indeed, the function vanishes outside of A and vanishes out, Fourier transform vanishes outside of B, we get that the function is. So Amrei and Berthier, I think they didn't know about Benedicks, and they proved a bit stronger theorem, more general theorem. They were doing some operators, spectral theory of operators, mathematical physics stuff. But in this formulation, the theorem easily follows from Benedicks theorem. This will be in the homework, that if you assume that it's not true, so somehow you can come to contradiction, which will contradict to contradiction with Benedicks theorem using just some compactness factor. That's why I wrote exercise. You don't need to repeat the proof. You simply need to use it. And when it comes to this constant, this is what Kulikov-Nazarov proved in his PhD thesis 30 years ago, or a little bit more than, say, this constant. This is sharp, except of the choice of numerical constant. So that's all what I wanted to say about Benedicks theorem. If you have questions, please ask me.
so what are the extremals for these sets A and B? For this, like what are the bad sets or good sets in Nazarov's theorem?
This I need to think. Just a second. No, it's spot. I cannot tell you. I know. Just a second. Give me a second. If
Maybe something that gives exponential growth would.
I need to think, Alexei. Let me leave it, and I will, if you will be, I will update a little bit my notes and will write what is extremal in my notes and will ask you to pose to replace it. But I need to think.
I have another
Yeah,
question.
I meant just like something that gives exponential growth, not the sharp like one, but just.
Rostislav, what did you said something?
Yeah, I wanted to ask.
Yes.
Sorry. Sorry. Yeah, Rostislav.
Yeah, okay, thank you. My question was, if we fix A, how much freedom are there for B? So is the choice of these two sets support?
Yes. So in reality, the only thing which I can tell you that in reality we didn't use that both sets had a finite measure. So if you look what the proof used, and there are many other interesting examples. So the proof used only that for almost every x in TD, the set support of F intersecting with shift is finite. And the same that for almost every side in TD, support of F hat intersecting with ZD with side is fine. So in reality, it's about translations and colors. There are many other beautiful examples like hyperbolas. You can create other examples. If you look at the proof used only this. And the measure entered as the size of this sets. It's not exactly what you asked, but this is what I can tell you, at least without thinking.
Yeah, thanks. But in general, it's interesting if we have fixed the support of F. So A is fixed, and we look for all F1 functions, L1 functions with support in A. What can the support of its Fourier transform be?
So it's very much depends. You enter dangerous waters. So it's very much very modern. It's very much depends on fractal structure of A, or the structure of A. So if A is a like Cantor set taken inside out, if set A has some structure, then a lot can be. This gives you other restrictions. So some arithmetic conditions on the set A can give you other restrictions. So this is a delicate issue already. I'm not I put some in my notes. I put some references in the very end. I call them suggested readings, so you can look there. But this is already maybe I will upgrade a little bit, but I cannot tell you on 1 foot. I cannot tell you too much. So.
Thank you. I'll be cautious not to enter very deep water.
No, it's nice. It's nice to enter deep waters. It's always good. All right, so I erase the proof. So we will jump. So Benedicks proved his theorem in 1974. Though he published it, I think, only 10 years later. This was usual for this guy. Both me and Alexei know him well. He's a very deep mathematician, but he never is eager to publish fast what he does. Unless he works with some young people, so he feels pressure. But this was an old tradition in Swedish mathematics, but which probably disappeared these days. Leonard, I heard once a lecture of Leonard Carlson, and he told that he was thinking 13 years on his proof that Fourier series of L2 function converge self-positively. So he said that it took him 13 years just to think about it. So now we will jump 45 years and come to result of Danila Radchenko and Marina Viazovska. Which says the following, that they proved that these two sets well, if we deal with is a uniqueness pair for even part of the Schwartz space. So if you have an even function from the Schwartz space S, which vanishes on this set, and Fourier transform vanishes on the same set, then the function is identical. And if you have arbitrary function, then you need to write, I will do it. If we deal with S of R, but then you need to add on the spatial side, you need to add two values. Also, these two values should vanish in the general case. So what Radchenko and Viazovska used in their proof, they found a beautiful interpolation formula which recovers the function f by its values, or even function from the Schwartz space by its values on the set and values of the Fourier transform on the same set. So it also gave quantitative version of uniqueness, but their interpolation formula, it's pretty deep result, because their interpolation formula used modular forms. It's very, in spirit, it's very similar to sampling formula which Warren told you for functions from Pelley-Wiener space. But there, the basis function are sine x over x, or sine pi x over pi x. In their situation, the basic functions were modular forms. And that's why this was quite unusual, but this was amazing result, really amazing result, which immediately took attention. Many people from different areas jumped, because there is no hidden Poisson summation, no hidden analyticity, which we used. I remember visiting Kharkov. This was that year, or maybe year before. I learned that I knew about, or they posted an archive earlier. I met Vladimir Alexandrovich Radchenko, and he always asked me what's new in mathematics, and I told him about this, and he jumped and he started to shout, "Why people tell me that all interesting things are only in topology and algebraic geometry? In analysis, there are also beautiful new things." So really, what I can tell you is that everyone was very much surprised looking at this. And then there was a different proof, which recent proof, which Gabriele Gautier and Venkatesh gave to this result. They didn't use, Venkatesh is another field prize winner. They didn't use modular form in the interpolation formula, but they used very heavy representation theory, modern heavy representation theory and theory of Fuchsian groups. And certainly it was a change for people in analysis, because this is a result, clearly this is a result in analysis. It was a challenge for people in analysis to find the analytic approach to this result. This is what we took. We took this challenge with my colleagues. So first with Mikhail Nazarov, and then Alexei Kulikov joined us. He was before student of Christian Seif. Trondheim. So punchline, we didn't succeed to prove their theorem, but we succeed to prove what they couldn't do. Their theorem is very rigid. You cannot change slightly. You cannot shift these points. Arithmetic nature of these points was very much important in their proof. So their proof was very, very rigid. You cannot do, because it's the same with the proof with which Venkatesh gave. Maybe I will formulate first what we did, but then I will prove it in a toy model case which gives an idea about technique and when the proof is simple. So supposedly, let's enumerate our points. On the one end, they go to minus infinity. On the other end, they go to plus infinity. So we call that we are in a supercritical case. If lim sup of and the same for Ramos. And subcritical case if lim inf of the same expressions is bigger than 1. But the Radchenko-Viazovska pair, it's a simple computation, it's exactly 1/2. So what we proved, you can easily guess now that in supercritical case, it's uniqueness pair. In subcritical case, it's non-uniqueness. So this uses purely analytical tools, and not very difficult, but the proofs are quite long, and I gave reference. Both I suggest very much. Radchenko-Viazovska paper, it's deep, but it's readable. They explain what the use of modular forms. Just they use a standard functions, not sine, but some different functions. Our proof uses only elementary tools. But what I will do now, I will prove uniqueness part of our result in the toy model case. So instead of lim sup, I will write here maximum.
So before we go in that theorem, it's uniqueness pair, but for which space? Just Schwarz functions? Or...
In our situation, it's better. It's even Sobolev. It's for the space H, and also in this theorem, these are functions f such that and the same on the Fourier side. Well, it's redundant to write all four integrals. So usually Sobolev space, if you assume only this, and I assume on both sides. But we use, our approach uses only first derivative. We don't need. In Radchenko-Viazovska case, they use many derivatives. Maybe not Schwarz, but probably 17 or something like this. But this was technical. I think one can improve this. Then lambda gamma. The proof is amazingly short. And by the way, the proof, okay, let me. Let's take A less than 1 such that left-hand sides are less than well, we have 1/2, so we have some support. We can consider this interval. Let us split it. Let us take maximum we are outside of the integral. So we want to show that our function, this is a uniqueness pair. So we assume, meanwhile, that f on lambda equals 0. I don't assume meanwhile that f hat lambda equals 0. Then I will use Wirtinger inequality, which Oren proved by my respect, by my request. Sorry. So in classical, in usual Wirtinger inequalities, 1 over pi square, but we need to rescale, so it will be length over pi squared, and here integral. Well, now, because of our assumption, all this is less or equal than a square over 4 pi squared. This is our density. Well, what's written here is square over 4 pi square integral over half. If we return to the Fourier transform, it will be a square psi square. So now look what we get. We started with this integral. We get this bound with some coefficient which is less than 1, assuming that function vanishes on lambda. But our assumptions are completely symmetric. Now, if we assume that f hat vanishes on gamma, then repeating the same argument, we will get that the opposite inequality. So what does it tell us? It tells us that both integral vanish. So function is identically 0 and we are done. It's really amazingly simple.
But it's sort of really important for you that the sharp constant is really 1 over 4 pi, 1 over pi squared, or 1 over 4 squared, right?
Yes. What Alexei hints that this proof, because we know how extremal function looks in Wirtinger inequality, that here we can write. We need to modify a little bit. We need to look where we use how we Wirtinger inequality, everything else, and this will give you the same proof. And what is unfortunate that, look, what is the difference between uniqueness part of our theorem and this result? So here we have upper limit. This is a normal formulation. We have asymptotic assumption, but we have a supply here. I wrote here less than 1 half. So if we move, we have infinitely many extra points. So if we move finitely many points which are away from the bound, so we have this condition, but it starts only far from the origin. Usually we get used to the fact that we can move finitely many points in any position we wish. But here we cannot do this. So our paper, our uniqueness part is 30 pages or 25 pages long. And all of this is about moving finite amount of points. So I still have a feeling that maybe someone who is more clever than we are will find a way. So this is, really, it would be nice if someone would think about it. So what I'm saying, some critical cases is a different matter, but I don't have a simple reduction of our uniqueness theorem for this way model. We're still using the proof Wirtinger inequality. Ideas are similar, but technically we need to use also Fragment-Lindelöf, a lot of analytic function theory. Technically, proof is much more complicated. It's very weird, but what can I do? And now let me to finish.
And so in the second part, it means that you construct example which vanishes on many.
Yes. And the second part is different. The second part is based on some entire function theory, also quite classical stuff, which was known, I don't know, 70 years or 80 years ago, some Kharikov type mathematics. But Kharkov of my time, not of time you got it back. But we constructed a function which values on both set being not identically zero. This function is even entire, so it will be entire. Maybe I want to tell you a few more things. So you can get quantitative version, but for this you need to assume a little bit more. So let me give you a definition. I will say that the sequence lambda is separated if lambda j plus 1 minus lambda j, we get rid of some positive constant over 1 plus minimum. So we can always, if we are in subcritical case, this means that these guys cannot be too small. And here, so it's opposite direction. And because we have here surplus, we can always remove. If we have if we're in a supercritical case, we can always take a subset such that it will be still in the supercritical case, but it will be separated. So this is not an extra assumption. So what I'm saying is that if lambda gamma are supercritical, then there exists also this is a simple exercise. But why I'm telling you this is that suppose that lambda gamma is separated uniformly supercritical. By this I mean, by uniformly supercritical, I mean these assumptions. And H is our space, then there is constant, numerical constants. Is smaller than the infinity side, we have the function f from our symmetric Sobolev space. A times the norm. So you can say functions are small, then the norm is small as well. And what is written here, pay attention, it's funny, nice, and it gives a heuristic on what's going on. That what is written here, it's a kind of Riemann sum for this improper integral. But only I have don't need to write. I will check and I will change in the homework. I don't need the squares here. in my notes there is a mistake. If you have a, if you want to write a Riemann sum, then you have lambda square, but you also have length of the interval, lambda j plus 1 minus lambda j. And lambda j plus 1 minus lambda j, because of our assumptions, it cancels 1 power of lambda. That's why here, Riemann sum for the integral looks like this. But I will check it. And to prove this, the more interesting part is this inequality. To prove this again, you need to use Wirtinger inequality, but quantitative form, which Oren expected. And maybe to finish, if you want to practice, Wirtinger inequality is a very strong tool. So if you want to practice, here is one more nice exercise. So suppose we have a set gamma, and let us say that it is L dense if R minus gamma contains no intervals of lengths. So distances between each pair of consecutive points, so the set gamma is less than or equal than. So exercises. These are inequality which are probably new ones. So suppose t bigger than 0, gamma is 1 over 2t dense. Then for any alpha bigger or equal than 0, t to the power 2 alpha integral over r absolute value of r square. This is a kind of fractional Wirtinger inequality or fractional Poincare inequality, but only one dimensional. And another exercise which uses this, so suppose gamma is pi dense, then for any natural n, it's a Schwartz space, if function vanishes on gamma, then it's set to 1. It's bounded to normal density. At least I've never seen, I look at Hardy Littlewood Polya book, other books about inequalities. I've never seen these two inequalities, but this is a simple consequence of the Wirtinger inequality, the way I formulate it. All right, so it seems that's all.
Sorry, I missed. This is n's derivative norm?
Yes.
Okay.
Pi, because it's like sine pi. It's sine x. Sine x vanishes on pi z. It's pi dense, and when you differentiate sine z, you do not have any constant. And this shows that this is the best possible one. You can rescale, of course, but then you will get powers if you rescale. I don't know, maybe they will be useful for someone. I've never seen things like this. We didn't use this, we used in our paper. This we didn't use, just noticed it's relevant. But this is simple if you understood this proof, these are simple exercises. All right, so maybe I will make, Alexei, maybe I will make right now 2-3 small updates in my notes, just add some literature and maybe write a comment for Roman about one-sided Hardy's theorem, because he's not here yet, right?
No, today.
That's all, and thank you. It was a pleasure to give you this course. Thank you for listening.